True or false? I said false. Because 0.997 is not 1.
Yeah.
That's plus or minus 3 standard deviations from the mean, but that is not all the data. And all the data equals 1. Okay, number 2. If they have the same mean, then the line of symmetry has to be the same. But different standard deviations mean the shape of the curve changes, right?
Yes.
Yes. Number 2. This one has the same standard deviation, which means the shape of the curve is identical. But they have different means. So I had to draw those curves in different places. How'd you do?
Just draw it up.
Okay.
You did okay. All right, I'll take okay today.
All
right.
So like how does that going to affect the curve?
No? Why is it no?
Because it goes past the next line.
Because it goes below. Very good.
Oh, yeah.
Number 2?
Darn it, I didn't
No.
realize the
No, why is it no?
Because it's double from the side of the whole curve.
All right, it's camel. It's not symmetry. Meh. Number 7?
Yes.
It looks beautiful. Number 8, why is it no?
It's not symmetrical.
It's not symmetric. It is skewed
left.
left. Excellent.
Very cool.
All right, 95% of the data lies plus or minus 2 standard deviations from the mean. That was so like something I would do.
Yeah.
That's why I laughed.
Around
I wasn't laughing at you. I was laughing because, hey, that's me.
Chair.
All right, the 2 parameters that we need to determine probabilities with a normal distribution. We need the mean and we need the standard deviation. All right, let's move on. Okay, now, this is where the rubber hits the road. Did you actually learn anything yesterday? So, for these, we start off with baby kind. So if we draw the mean and we add the standard deviations, this says plus or minus 2, so that would be from 9 to 21, plus or minus 2. All right, this is 2.5. So we would add, multiply by 2.5. Are we good? Or you could have made another little chart and added and subtracted 2.5. Right?
Yeah.
All right. 13 and 14. All right. So I drew it. I marked it. I looked at how far apart it was. This was 1 standard deviation to the left. This was 1 standard deviation to the right. Plus or minus 1 standard deviation. 68% of the data. So this asks for a probability. Should probability be written as a percentage? No, when they ask for probability, it's just a decimal. Right? Probability, decimal. Percentage, percentage. All right, this one. New curve, new mean, new standard deviations. So from here to here, here to here, 0.34, 0.34, 0.135. Add them up.
Yep.
Oh, wait. This one was actually a different number. I made up a new problem here. What if it went from here to here? That's what we would do.
They got this wrong.
Whoopsie.
Yeah, I know.
You got that one wrong? Oh.
I got that right.
I didn't.
All right. 95% of the data?
Yep.
That's plus or minus 2 standard deviations, right? So it's 20 plus 2 standard deviations, 20 minus 2 standard deviations. So my low boundary, my upper boundary.
What am I doing wrong?
Everything.
You could have.
No, I got one.
I drew on some. I didn't on others. Yes, ma'am.
Could you do like the P and then like 1948 is like,
It's not.
or like X is greater than 1928 or less than 20?
Oh, it's 68%. Yeah, see,
Could you do those or no?
but I got
On
You just
this
have to
one,
change it over.
on these 2, yes. There's your probability. On this one, this is the interval.
Yep.
So this one is giving you, we couldn't write that as a probability.
I'm really sad.
It'd be like that, so.
This one we sure could. We could write this as the probability that it's between 1970 and 2030.
68.
0.68.
So probability you want to put down like decimal.
Correct. Probability, decimal. Decimal answer.
They got the right answer as well.
Okay, every once in a while, there'll be a probability problem that asks you to write your answer as a percentage. That does happen. And in that case, you could. But normally, probability decimal. Okay. All right, so here we go. Lifespan of a tire, normally distributed, 30,000. Deviation of 2,000. So 30, 32, 34, 36.
Yep.
I got that one right.
Between 30 and 34,000. Awesome. So we're looking at a lifespan of the tire between 30 and 34,000. So it's the 0.34 plus the 0.135 is a 0.475.
No, you got it right, but you keep putting it in percentages and ask for the probabilities.
Oh, yeah.
Got that wrong.
Yeah, keep
Okay,
putting the
and finally, number 18.
What?
Here we find the probability. The probability is 0.16. And then we multiply that by the total to find the estimated number. So we take the probability for that interval, multiply it by the total, and that gives us the estimated number of students. Now, this one I didn't do any math for because 0.16 times 2,000 is the same problem I'd already done. And the reason that works is less than 5.3 is from here back. Greater than 1.7 is from there over. Aren't those symmetric parts of the curve? So it's the same area, which means the same probability. All right. So do we feel like estimating using the empirical rule is something we could do? All right. So,
For sure.
Okay, we can do some more practice. Actually, tomorrow night's homework, the first couple are about the empirical rule. So we'll touch that again. And I think tonight's maybe the first couple are about the empirical rule. All right. So the empirical rule gives us beautiful estimations, right?
Yep.
So those are estimations. All right. Then you had a little bit of review. Now, if you miss this stuff, then that probably means you don't know how to operate your calculator. Yes. Or it could mean you punched one number wrong. One or the other. So if you got most of them right and just a couple of them wrong. So in this case, we were asked to find, sketch a box and whisker. I apologize for giving you a number line that was numbered incorrectly.
It's okay.
45 wasn't even close to being on your number line. All right. So here we should have numbered them slightly different, so we could go out to 45. 45 really is looking like an outlier, just looking at the box and whisker. And when we use the IQR to determine, our upper boundary is 37, and 45 is beyond that upper boundary. So 45 is considered an outlier. All right, number 2. Obviously, this is a sample because it's just the first 20 consecutive shoppers. That might be like a convenient sample. I think that's a really poor sample because it could be that all of your contractors come in really early in the morning and buy the most supplies before they head off to jobs. And then throughout the day, people come in and just buy like one hammer, you know? So doing a convenience sample at a home improvement store might not be very reflective. But anyway, so that is a sample. So here's our data. It does look like we got one contractor in there, doesn't it? Okay, so why did I use X bar and S?
Mean and standard deviation.
Very good, of the sample. So we'll use S instead of sigma, right? Because this was a sample.
Yes.
All right. Okay, half of you are engaged right now. The other half are dreaming about summer. I get it. I totally get it. I am very excited about summer. I get to go see the whales, and then I get to swim with the manatees. It's going to be amazing. But right now, we need to focus on this.
Where's
Math.
some whales and manatees?
We gotta swim.
Two
with the
different
math
places.
Oh.
Yeah,
Going to
That's a wide
it is.
range
It
of
is.
aquatic creatures.
Yep. All right, so here we go. Leave the whales and the manatees and come back to math for a second. All right, now this one. If we go back to this data and throw out the outlier, now we've got to where we can look at the mean and the standard deviation. Okay? The outlier greatly increased our mean. See, our mean went from 55 to 43. Once we threw out that outlier, our standard deviation went from 55 to 17. Much smaller. Yes, ma'am.
Could you also say that the outlier decreased the mean and the standard deviation? Like it was a decrease without it?
Oh, without the outlier, it decreased. Yes, it sure did. All right, let me pause so I can answer the phone.
Oh my gosh, we're recording.
All right, so let's see. Oh. Ha-ha. All right, now let's take a look at these. Self-selected.
Yay.
Usually some bias.
Yep.
Cluster.
Bias.
Already because they already play sports. Simple random sample, that is our least biased of our sampling methods. That's a great way to do it.
Hey, wait.
Oh, dang it. So how would that like not be biased?
Played
'Cause, like
myself.
for me, I put it would be biased because only people being affected are being sampled. That was my reason for it being biased. So
I actually agree with your justification. Welcome to statistics. There is not one right answer half the time,
Wait, what did you get to?
depending on your justification and your approach to the data. He said there was some bias here because they only did the homeowners that were affected.
How about number 3?
And I kind of agreed with it. I'm like, oh, I could see that.
How about number 3?
Number 3? What do you think about number 3? You don't see bias?
Well, it says it's a I don't know how to say it out, but I just think it's Can you tell me where it's biased? Like,
A self-selected surveying method is almost always biased.
yeah, I know, but you can't like asking all of the customer that you
That's true. You couldn't.
Yeah, you don't sell the thing to them, so you can't ask for all of the
Yeah.
customer. But here he said he asked each customer, so I think it's that like he asked what he can ask that will respond to him. That
Okay. Just justify your answers. Explain why. All right. Now this one, X-rays. Obviously, I can't take you all and line you up, and we're going to do X-rays on your eye and see how that your vision changes. That would be bad.
you sure?
We can't do that. But
Fix my mess.
if you were already or if you had already had X-rays, we could compare you with people that hadn't. So that would definitely be an observational study. We can do an experimental with the gasoline additive, as long as it wasn't an additive that was detrimental to people's cars. That'd be bad.
Oh yeah, like sugar. You know you can run your car off of moonshine.
No, I don't happen to have any of that, so I've never tried
No,
it.
I'm just saying like
All right.
Mythbusters
Alcohol
did.
can do this.
Mythbusters.
It creates a
That's
lot
a
of
great
vapor,
show.
remember?
I love that show.
Yeah.
All right, are we ready?
Yeah.
So we still remember last week. That's what this page was. Do you still remember last week?
Everything except for the
All right. Today we're entering the world, and we talked about it yesterday. So far, we've compared apples to apples because that's all we could do.
Yes.
Today, we're going to learn how to compare apples to oranges. All right? Now, today is baby step 1 to actually doing real problems, but we have to learn some skills before we can apply them with the real problems. So I do want to talk about some really important stuff. A standard normal distribution. Now, we have already learned about a normal distribution. We know the mean, median, mode are all the same. We know it's symmetric. We know the area under the curve is what? 1. So we know lots of things about a normal distribution. So all of those things apply to this one. But it's special.
It touches.
For every, there's only one, so I shouldn't say every. We have infinitely many normal distributions, but there is only one standard normal. Standard means I'm standardizing the data so that I compare everything to other things. Now, what I do is I force the data to have a mean of 0 and a standard deviation of 1. So we're going to convert our data. Remember how we used to shift graphs around? We're kind of doing the same stuff with data. We are transforming our data. So we're taking our data and we're shifting it so that it all has a mean of 0. And then we're taking all those funky shapes for our curves and we're performing an operation on them, division right here, which forces them to all have a standard deviation of 1. So this forced the mean to 0. This part forces the standard deviation to 1. Now, what is this called when we do this? So what we're creating is a z-value. A z-score is what it's normally called. And that z-score is part of the standard normal distribution for a data set that indicates the number of standard deviations that the data is away from the mean. So, since we're forcing our data to have a mean of 0 and a standard deviation of 1 by converting the pieces of the data that we need to a z-score. And this is how we do it. Value minus mean divided by standard deviation. Now this part we're going to actually work on tomorrow. Tomorrow I'm going to give you some data and we're going to convert it to a z-score and then we're going to see what that means. But today we have to start working with a z-score because this is all brand new. Okay? So I'm going to show you how we work with a z-score now and what it means. All right. Did you pick up a table?
Yep.
Yes. Good. All right. So this is standard normal probabilities. So what we're going to notice is right here we have a z. What do you think that z represents?
Table entry.
Z-score. So this is a table that represents the z-scores. Now, the z-scores can be found by first looking down the column. And then the hundredths place of the z-score can be found by looking across the row. Now, when I find that number, what this number represents is the area under the standard normal curve to the left of the z-score. So, remember when we talked about area under the curve? We said the area under the curve is equal to the probability, which is the same as the percentage, right? So this area under the curve is going to be very helpful for us. So, you don't have these examples, but we are learning how to use our chart. So everybody should be looking at their chart now. You got your chart out? Now, I will tell you, these old eyes don't read like they used to. So when I read this chart, I give me a little purple, and it's my purple index card. I use it for everything. And I move it down the chart so I stay on the right line. Now the chart is shaded every other line, and you guys have young eyes, so you may not need to do that. But first of all, what is the area under the curve to the left of a z-score of negative 3.31? All right, what we're going to do is we're going to sketch the curve, and we're going to think about what that means before we do anything. What is the mean of every standard normal distribution? 0. And what is the standard deviation?
1.
1. So this would be 1, this would be 2, this would be 3. This would be -1, this would be -2, this would be -3. You don't have this. You're just watching. You're just watching right now, guys. All right. So where would -3.31 be? It would be somewhere over here, wouldn't it? So the area to the left of that would be really teeny, wouldn't it? That's not. I don't think that's a word. But I mean, I needed to use it so you could understand. It's very small. Okay. So now let's go back up to the chart and find that area. So this is the z-score we're trying to locate. Okay? We want -3.3, so we're on this row. This row. So that's what we're looking at. Okay? And then we want 1 to be our hundredths place. So 1 is our hundredths place. So what area is associated with a z-score of -3.31?
0.0005.
The z-score is 0.0005. Not the z-score. Hold on. I just wrote that wrong. That's the area under the curve. So the area under the curve corresponding to a z-score of -3.31 is that. That's the way we should have written it. Now, on this one, because this always gives us the area to the left, this is a z-score that is less than, because we're looking to the left. Okay? In a minute, we're going to look to the right and talk about what that means. Now, does this make sense? Does 0.0005 make sense for this tiny little area, thinking about what we know about the empirical rule?
Yes.
When we think about the empirical rule, out here is 0.0015, right? So that would be all of out here. Well, this isn't all of out here. It's even part of that. So is this number smaller than that number? Does it make sense?
Yes.
Yeah. All right. Let's look at another one. Now we're going to find the area under the curve to the left of -0.28. So this is 0, this is 1, this is 2, this is 3. This would be -1, this would be -2, this would be -3. So because it's a standard normal, that's what we're looking at. A z-score of -0.28. That's almost a third of the way, right? Third of the way. So that would be like everything to the left. So everything under the curve over here. All this stuff. Y'all see? So do you think that area is going to be bigger than our last area? Oh yeah. All right. What if it were 0 instead of this? If it were 0, wouldn't that just be half the curve?
Yep.
And it would be 0.5. So this might be close to 0.5 because it's close to 0. Let's go see now. All right, let's use our chart. -0.28. So find the -0.2. You find it on your chart.
Done.
Okay? Now go over to the 8. All right, there's the 8. So this should be our answer right here.
Yep.
So the area that corresponds to a z-score to the left of -0.28 is 0.3897.
So this is our formula, right? Like in the quiz we'll use this, right?
Yes, you'll have to have the chart on the quiz. Okay, so you try. example 3. So all you're doing, guys, is you're just using your chart. Now this Z-score is positive. Do you notice that on your chart, one side is negative and one side is positive? I really wanted to run them all side by side, but my vision has diminished over the last year, and I can't read them side by side, so I wouldn't be able to help you. Y'all probably could, but I can't. So y'all have to do front and back. Sorry.
So when we're doing these, we don't have to draw a picture. We really don't.
Oh, I didn't get the right chart.
What?
This isn't the right part of the chart.
You need more.
I need 1.82.
We have
Down a few.
You have the chart though.
You have the chart.
Yeah.
All right, you read the chart and you tell me what it is, because I can't even look.
0.9656.
0.9656. Okay, so this is the area where the Z-score is less than 1.82. Now, let's see if that makes sense to us. If we did this, 1.82 would be about right here. That does look like it's a lot of the data. Yeah. Does look like it's a good bit of the data.
Yep.
Woo. All right, so that does make sense. Okay, now these are actually on your notes. So now we should be pretty good with this. So when we have these problems, I want you to just sketch a little curve. It doesn't have to be beautiful. But we're going to find the area under the curve to the left of 0.99. Before you ever start, we could do a really good estimation of this. Isn't negative 0.99 really close to negative 1?
Yep.
And don't we know from the empirical rule that this is 0.135, this is 0.0235, this is 0.0015. So from the empirical rule, we can estimate that this is really close to 0.16. We could give an empirical rule estimate. Now, let's find a more exact answer. So to find a more exact answer, let's take the Z-score, look at your chart, and find the area under the curve that is associated with a Z-score of negative 0.99. See if I can find the chart. Okay. Did we get 0.1611?
Yes.
Yes. This is exact. Was that a pretty good estimate we had a minute ago, though? That's a pretty good estimate. That empirical rule is not too shabby. That's a good estimate. All right. Now, let's read this one. Find the area under the curve to the right. Oh, that's new. To the right. Okay, so let's see what that would look like visually. All right, so 1.06, like just past here. And this time we're doing to the right. So I have to go this way. It's this part. All right, but when I look it up on the Z chart, it gives me this part. Very good. We could subtract it from 1. Okay, so when we're doing to the right, you can do 1 minus the area for the Z-score to the left, less than. because the total area under the curve is 1. So if we found this, subtract it from 1, it gives us that. So here we would have 1 minus, very good, 0.8554. And what do we get when we do that? Yes, we do. 0.1446. Now, that is one method. That is one method. Okay? There's another method. Okay, what do you think?
Can't you just look at the negative? The opposite?
Yes, you can. Is that what you were saying?
Yeah.
Just look at the opposite. If we look up negative 1.06 right here, it gives us this area. Is that the same as the green? Yes.
Wow.
So, when you're doing the right, there's 2 ways you can do it. You can either do 1 minus, read that number, or we can just look up the area that is less than the opposite of that z-score, because the normal distribution is symmetric. I want everybody to actually look up negative 1.06 and see what you get. Don't just believe me. 0.1446. Are they the same? Yes. Wow. Okay, now let's talk about how we would do between.
Whoa.
Okay, so first let's draw it so it'll make sense. So we have 0, 1, 2, 3, negative 1, negative 2, negative 3. All right, so this wants us to go between negative 2.16, right there, and negative 1.3, right there. Okay, so negative 2.6 and this. All right, let's see. Let's start with the bigger one. If I found the area to the left of the larger z-score, it would be that whole thing, right? I don't want that whole thing. I just want the part in the middle. How do I get rid of that tail?
Subtract it from to the left of the 2.
Very good. So if we took the area of the z-score that is the larger one, and we took away the area to the left of the smaller one. I left out my negative there, sorry folks. So you do the larger minus the smaller. When we take away the smaller, let's take it away. Look what we're left with. What we wanted. So the larger minus the smaller. So when we look up negative 1.35, what do you get? 0.0885. Now let's look up negative 2.16.
0.014.
Is that what y'all got?
Yes.
Okay. So when we subtract these two, we get 0.0731. All right. Now, I didn't run off any more examples, but I do have a few more examples. Now we're working backwards. This time I'm giving you the probability. The probability is the same as what? The area under the curve. So this time I'm giving you the answer of what we just did, and we're working backwards to find the z-score. So if I ask for a probability of 0.2236, 0.2236,
0.76.
You're faster than me.
That's so funny when you go from negative.
Okay? So, if we look, this is inside the chart. And we work back out to find the z-score. So the z-score is negative 0.7. And then we look up, what is the last decimal place? 6. Okay? Now, could I have looked at this number and known it was on the negative side of my sheet?
No.
Yes.
Yes.
You can. Because the negative side are the probabilities that are less than 0.5. And the right side would be and the positive side would be the probabilities that are greater than 0.5. So what do we need to do for example 2? Flip it over. So now we're looking for, oh no, I don't see that exactly. You do?
0.03.
Yeah.
Oh, it is 0.03. The next one's the one you don't see.
I'm gonna find it.
Yeah.
No, I'm not gonna find it. Yes, I am.
Just find it. Just round it down.
Okay. So, the next one. There isn't a 0.75 that I can see straight away.
That's right.
There's an area of 0.7486, and that z-score is 0.67, and then right beside it is 0.7517, and that z-score is 0.68. 0.75 is kind of in between, isn't it?
Yeah.
Not exactly, but close enough to exactly to where we can just say, all right, what's in between?
0.675.
It would be a z-score of 0.675. And actually, I'm going to go ahead and say, hey, I approximated here. All right, last one is kind of interesting. If I ask you for the lower and upper z-score associated with the middle 40% of the data,
What does that mean?
okay, what does that mean? That means I need to draw a curve, okay? And I need to think about, because I'm not going to know exactly where this is, but I want the middle 40%. So I'm going to say the middle 40%, I know it's going to be less than 1 standard deviation, so it would be something like that, because the middle 68% is 1, right? So it's somewhere in between here. Okay, so if this is 40% of our data, how much is outside of here? 60. So how much is at this end? 30. And how much is at this end? 30. Whoops, that's 300. I was going to do a percent. It got really big. All right, so this right here would be 0.30. No?
So,
Why would it be 300?
300.
So 30% of the data?
Oh, yeah, yeah.
Yeah?
Yeah.
So this would be 0.30?
Yeah.
Okay, so can you guys find the z-score? It goes with 0.30?
Yeah.
I drew it in the wrong place. I should have put it right here. This is the area. The area is 0.30.
0.3821.
130.2981.
0.5.
It's like negative
Like
5.
Is it 0.617? 0.5.
It looks like 0.30 is kind of halfway in between negative 0.52 and 3.
Yeah.
Okay, so, yeah. Okay? So that would be our lower one. Negative 0.525. So what do we know about symmetry? What would be the upper one?
The same, the positive.
It's the positive. 0.525.
Like magic.
Like magic. All right. So the back side is your homework, and it's a little bit of review from empirical rule, and then the new stuff. It should go pretty fast. It's just reading the chart. Can you read the chart?
Probably not. Probably not.